Hello everyone. In this video, I will introduce our recent research work regarding out-of-distribution detection for softmax-based classifier. Our method is based on generalized entropy, which is simple but effective. So why do we need OD detection? Usually when we deploy the deep learning-based models into the real world, the input images could be diverse, meaning it can be different from our training images. Therefore, to ensure the reliability of deep learning-based models, in particularly for high-stake tasks, such as medical image analysis or autonomous driving. Therefore, deep learning-based models are expected to differentiate in-distribution samples and out-of-distribution samples. Basically, a model should know what they don't know. Here is an overview of generalized OD detection tasks. The first column represents sensory anomaly detection. The goal is try to differentiate images that has a different style compared to the training images. The second and the third column represents novelty detection. Their goal is try to differentiate images that has a different class compared to the training images. The fourth column represents open set recognition or OD detection. Their goal is try to detect images that has a different class compared to the training images. Meanwhile, they need to guarantee the classification accuracy of the in-distribution samples. The last column represents outlier detection. Their goal is try to differentiate the minority images in the training images. Usually, outlier detection is regarded as a pre-processing step to obtain a clean dataset. The above-mentioned 5 tasks can be classified based on the distributional shift of the input images. Shift meaning the label the data distribution of the training is different from the data distribution of the test dataset, such as style change or adversary examples. In this work, we focus on classification-based method for OD detection. It requires a softmax or a pre-trained softmax classifier. Post-hoc method. It aims to design a suitable score function to distinguish in-distribution samples and out-of-distribution samples. Another method is enhancing method. It modifies feature from intermediate layers to enhance OD performance for a given score function. The third method is training loss modification. It usually incorporates OD samples in the training procedure to perform OD detection. In this work, in particularly, we focus on post-hoc methods. Here is a standard classifier. Some methods use information only from the feature space, such as Mahalanobis distance or NUSA. There are also methods that use information from the logit, which is max logit and energy. There are also some methods use information from the probability space, such as MSP or KL matching. The merit of post-hoc method is overhead cost retraining is avoided. There are also some methods combine information from the feature and the probability space, such as grand norm and the predictive normalized maximum likelihood. There are also some methods combine information from the feature and logit, such as virtual logit matching. In particularly, the assumption is in-distribution test samples close to the training data are expected to result in a confident prediction. To increase the robustness of our method of truncation operation, probabilities. Our goal is designed to capture small entropy variations in the top M classes. So our final score reads as negative generalized entropy, sum over from the top 1 to top M classes. It can be seen in the first 2 figures. When we usually choose M equals to 100, we could achieve pretty good results in terms of both AUROC values and FPR 95. Moreover, usually we can just set gamma equals to 0.1. It can be seen our method could achieve best results or pretty good results in terms of both AUROC values and also FPR 95. Here is an average results of our method. The first block is post-hoc method. It can be seen our method outperforms all the other methods on average. The second block represents method requiring training datasets. Again, our method achieved the best results. To conclude, our method uses probability information only. Moreover, it doesn't use any training data statistics. It doesn't require retraining or outlier exposure, but it still performs very well across 4 different datasets and 6 architectures, meaning it can be potentially used in more constrained model deployment scenarios. Thank you.